Hello everybody, today starts section 1.3 in our workbooks, and that is found on page 61. So if your workbook is not open yet, let's just take a minute and all open up to page 61. And if you notice, I've actually already gotten a jump on the type 1. So I have my pencil here, and I'd ask that you put your pencil this way on the paper, and above domain, notice what I wrote, and I hope that when you see L, R, you're thinking, oh yeah, we used to always write above the word domain L, R to remind ourselves that we're going to come in from the left, and then we're going to come in from the right. So I take my pencil, and I come in from the left, and I stop when I hit the graph, which is right there. Bam! Hit the line, so I stop my pencil. And then I say, well, is this -1, -2, -3? But then I see I hit an arrow, which reminds me that when I hit an arrow, it means that this line is going to keep going forever and ever and ever, which means my x values are going to go this way, to the left, forever, which is towards -infinity. So my domain, when I go to write that, I'm just going to undo this real quick. Coming in from the left is -infinity. We can never equal -infinity, so that gets a parenthesis. I just came in from the left, and so now I'm going to come in, I am going to come in from the right side. So coming in from the right, I stop when I hit the graph, and there again, I hit my graph, so I stop my pencil, and then I say, where am I on the x-axis? So I look down, and at first I might think, oh, it's at 6, but then I see again that I hit this arrow. So once again, we can mentally imagine that this line goes this way forever and ever. And when we're talking about x values, to the right forever and ever and never with an end, that's not our bell. So just wait one sec. To the right forever and ever is positive infinity. So for my second value, for the domain, it's going to be positive infinity. Writing the positive sign is optional. When we were in the section before, first doing domain and range, some people liked putting the positive sign. It helped them keep track of which is which, so that's totally up to you. So coming in from the left and right, -infinity to positive infinity. On your own, please use your pencil and find the domain of this second line. Again, left and right. And I'm hoping very quickly we're saying, hey, check this out. Same thing when I come in from the left, and then when I come in from the right, I hit arrows in both directions. So for this line, it will also be -infinity to positive infinity. And then we have this challenge question. It says, can you draw a straight line, a linear function, that has a restriction on the domain? And you have a little space here if you want to try some sketches. But it says, note, no open or closed circles allowed. So it's like I can't say this is a line and then put an end on it. You're not allowed to add open or closed circles. So if you can come up with a line, I would love to see it in class tomorrow. But the reality is it is impossible for us to draw any kind of line with a restriction. So for all linear functions, I'm going to highlight this keyword. For all linear functions that look like f of x equals mx plus b, the conclusion for the domain is -infinity to positive infinity. Or, starting today, we're going to introduce a symbol that means all real numbers. The way that you draw that is two lines kind of close together like that, and then finish making an R symbol, like so. That symbol means all real numbers. So you have an option between using -infinity to positive infinity with interval notation or using the all real numbers symbol. Now let's take a look at quadratics. We just finished looking at linear functions. Now let's talk about quadratics. So once again, we're asked to find the domain and range. So I'm going to put L, R, and I'm going to move my pencil. Go get my pencil from over here and bring it down to these two. I would ask you to find domain and range of both of these, I'm going to pause it to give you a second to do so, and then I will rejoin you and see what you got as your answers. And I am back. Let's see how we did for domain on these two graphs. Coming in from the left, I stop and I hit an arrow. Now, at first, some of us might think, well, this is going up. That is true that the shape of the graph is continuing up. So if I were talking y values, I would say positive infinity, but we are talking domain, which is x values. So you kind of have to envision, as your graph continues this way, yes, the y values get positive, but your x values will continue to go to the left forever and ever, which is negative infinity. So the left side for the domain is negative infinity. Then I take my pencil and I come in from the right. Coming in from the right, I hit positive infinity because this arrow means that yes, as my y values get more and more positive, so do my x values. So the right side of the domain is positive infinity. For the graph on the right, the process repeats. Coming in from the left and the right, take my pencil, come in from the left, I hit an arrow, which means negative infinity. And then when I come in from the right side, coming in from the right, I stop. Now this is an example where at first I might think this is decreasing. And if we were talking the y values, you'd be correct. Down for the range, going down forever and ever would be negative infinity. But once again, we are paying attention to x values. So the x values are forever and ever and ever getting more and more positive. So that is why, even though the graph does appear to be going down, that's about the y values. Our x values are headed to positive infinity. So once again, here's a challenge. Can you draw a U-shape or a quadratic function that has a restriction on the domain? Once again, you have that restriction. You're not allowed to add any open or closed circles, which means I can't go like this and like, oh, hey, check it out, there's a restriction. Nope, can't do it. No open or closed circles. If you can draw that shape, you are accepting my challenge. Show me what you got. But for the sake of the notes, I will establish that for quadratic functions, which are of the form f of x equals ax squared plus bx plus c, no matter what u shape we draw, if it's opening up or it's opening down and it's super skinny, doesn't matter what u shape we draw, we will always hit arrows coming in from the left and coming in for the right. So negative infinity, D for domain first. The domain will always be negative infinity to positive infinity, or we can draw that R shape, the two straight lines, R, which means all real numbers. So in our warm-up, we have established that linear functions, lines, increasing or decreasing, and quadratic functions, whether they open up or down, have no domain restriction, all real numbers. Let's see what's going to be different about this page. At the top, you can write skip. I'll talk about this with you in class. Let's see what's going to be different about even root functions. I'm going to highlight this title so it stands out. Domain restrictions, even root or radical functions. And this is on page 63. We are asked to write the domain for each of the following root functions. We notice these graphs look a lot different than our linear functions or our quadratic functions. So let's see what we discover about them. I'm going to get my pencil on the paper because we're asked to find domain. So we're going to be coming in from the left and the right just like we did for the warm-up. So above domain, I'll put left, right, right. Coming in from the left for our very first graph here, I come in from the left. I stop when I hit the graph, and hey, check it out. Hit the graph right there, so we stop. And then we ask ourselves, I'll make a note, domain, where am I on the x-axis? So here, I ask myself, where am I on the x-axis? I'm right here, which is at 0. So I put 0. It's a solid dot, so I put a bracket. Coming in from the right side, stop when I hit the graph. At first, I might think 18, but I know that it's not 18 because this arrow goes forever and ever, which would be positive infinity. We can never equal positive infinity, so that gets a parenthesis. Coming in for the second graph on the right, the process repeats. Coming from the left, this time I hit an arrow, which would be negative infinity. And then coming in, this was coming in from the left. Now coming in from the right, I hit another arrow, so that would be positive infinity. When it's negative infinity to positive infinity, remember you have the option, all real numbers. Now we're asked to consider which of these has a restriction. So let's take a step back and consider the difference. When I look at the type of function that it is, this one is a square root. And it's called a square root because we have an invisible little 2 right here that we never actually write. In general, 2 is an even number. So let's actually label this one even root. Here, this one on the right is a third root. 3 in general is an odd number. So we're going to use this to generalize a conclusion about odd roots. So when I look at this in general, even roots versus odd roots, the even root did have a restriction, the odd root did not. So even root. Even root function had a restriction. That is a big deal because we'll know right away. If I see a square root, a fourth root, sixth root, any type of even root, it will always have a restriction. And if I notice, the graph does not continue over here. So no x values from this side are okay. That's what we mean by a restriction. Not all values of x are possible. But when I go look at the odd root, this is going to go to negative infinity forever and ever, and positive infinity forever and ever. No restriction. All x values are possible for these odd root functions. On the other hand, if I look one more time at the even root, notice I clearly have a restriction. No x values from this side are possible. Let's look at numbers 1 and 2, and first see what connection we can make from the graph to what the function looks like. Right off the bat, I see square root, square root. So both numbers 1 and 2 are examples of even root functions. Let's from the graph get our domain. So I'm going to go get my pencil, bring it down here. When I come in from the left, I'm going to stop when I hit the graph, and I hit the graph right there. And I ask myself that question, where am I on the x-axis? So on the x-axis, I'm at 5 with a solid dot, so that gets a bracket. Then I come in from the right side, I stop when I hit the graph, I run into an arrow, which means to the right forever and ever, which would be positive infinity. So here's my answer. But what if I wasn't given the graph? What if I just knew this function? And I think, oops, hold on, that's a negative 5. So let me fix that. My apologies. On my screen it looked very small. -5. Let me go back here. There we go. Okay, problem solved. What connection can we make between why this says -5 to infinity and what I see with this function? What happens if we say f of -5? Let's explore that. If I let x be -5, underneath the radical where I see x, I will write -5. And then that's -5 plus 5. -5 plus 5 under the radical is 0. Interesting. The square root of 0 is 0. Check. What if I try picking something to the left? Remember we said there's literally no x values on this half of the graph that are part of this line. So let's see what happens if we choose one of those. Let's say -10. I would get -10 plus 5 under the radical, which equals the square root of -5. Can we do that? If you take out your calculator right now and you try square root of -5, what would you get? It would tell me error, because we cannot take the square root of -5 and get a real number. So we would say no solution. And tomorrow, as part of our bell ringer, we'll explore why we cannot take the square root of negative numbers. But for the purpose of our notes, we're going to establish from our 9th grade knowledge that it's not possible to take the square root of a negative number and get a real answer. So notice, as soon as I tried picking a value from this half where I don't see the graph going, it fails. We can't take that square root. So -5, this value from the domain, was actually the smallest possible x value that I could use, because I can take the square root of 0 and that's okay. But anything to the left didn't work. So how do I say that what's under here can't be negative? So I'm going to put that in quotes. Underneath radical can't be, can't be negative. We just established that. But I also want to say that but can equal 0, because that was okay. We could take the square root of 0. So how do we use math to say that underneath this radical sign can't be negative, but 0 is okay? The mathematical statement we are going to say is that x plus 5 can be greater than or equal to 0. So with this or equal to, I am incorporating that it can equal 0. And the fact that I'm saying greater than 0, well, greater than 0 means not negative, positive. So let's see what happens when we solve this. I'm going to draw a line down my inequality sign, just like I would an equal sign. And I have a one-step equation, or excuse me, a one-step inequality. I'll subtract 5 from both sides, and I get x is greater than or equal to -5. And I'm going to use this inequality to make the statement that my domain is all real numbers, x greater than or equal to -5. After making this statement, I ask you to compare what we wrote in these two boxes. And my question is, does this and this mean the same thing? Well, let's see. If I were to draw myself a little number line here and I put -5 on it, and I asked you last year to graph x is greater than or equal to -5 on a number line, the greater than or equal to part would tell me that I need to draw a solid dot, and then greater than means shade to the right. Then I look at this, and this says -5 to infinity. Here's -5, solid dot, so I can equal it. And then to the right, forever and ever, is infinity. So these, you don't have to draw this arrow, but I just want to make it stand out. These two mean the same thing. So the domain that I obtained from the graph, remember this came straight from the graph, matched what I got algebraically just using the function. Which is a very important point to make, that I technically didn't need the graph to get the right answer. So let's pretend for number 2. Let's pretend for number 2. Notice, I'm not showing myself the graph at all. So almost, if you wanted to, like, cover it up with your hand so you can't see it. All I have access to is this function. Let's apply what we did algebraically. So I'm going to take what's underneath the radical. In fact, I'm going to circle it. And I'm going to set up an inequality. I'm going to write x minus 2 is greater than or equal to 0 and solve. I'm going to add 2 to both sides. Draw a line. And I get x is greater than or equal to 2. And after getting x is greater than or equal to 2, we can actually now use that to write the domain. So the domain is all real numbers where x is greater than or equal to 2. And I'm going to put that in a box. Now me physically on the screen, I've been hiding the graph from our video, and I said put your hand on it so you can't see it. Now let's go look at the graph. If I just gave you this graph and I asked you to find the domain and range, you would come in from the left first, stop when you hit the graph. That is at 2. It's a solid dot, so it gets a bracket. And then when I come in from the right side, coming in from the right, I stop when I hit the graph. It's going to the right forever and ever and ever. So that's going to be positive infinity. So let's see if what we got from the graph and what we got from the algebra match. Greater than or equal to 2 on a number line, I would put a solid dot and shade to the right. Does that mean the same thing as 2 to infinity? It does! It's so exciting, right? Because it's 2, and then 2 as the starting point, and then to the right, get my hand to match, right, forever, you get what I'm trying to say, 2, and then to the right, forever and ever. Sorry, on the camera it's backwards, but towards positive infinity is this direction. So what I get from the graph and what I get algebraically are exactly the same answer, which is really exciting because we're not always going to have access to the graph. So to summarize our first 2 examples, whenever I have an even root, we focus on what's underneath the radical. So I'm going to write this down. Steps. I don't like it being in red. I'm going to change it to purple. For even roots, circle what's underneath the radical, like we did right here. We circled x minus 2 because that was under the radical. Set greater than or equal to 0 and solve. Those are our 2 key steps for finding the domain of even root functions. And what I ask you to do is now go and look at numbers 3, 4, 5, and 6. 3, 4, 5, and 6, and you try. So part of tonight's flipped homework is you taking a couple minutes right now to apply those 2 steps. And I'm going to show you just how to set it up for number 3. So again, just to clarify, I'll be looking for your effort to apply our two steps to numbers 3, 4, 5, and 6. All of these are even roots. Square root, square root, square root, square root. Step 1 was to circle what's underneath the even root. And then step 2 says, take what's underneath, in this case 2x minus 8, set it greater than or equal to 0, and solve. Your answer for the domain is going to be all real numbers, and then I'm kind of leave like a little box here, because it's whatever the result you get from your solving is going to go right there. So if you need to rewatch example number 2, go ahead and do that. But to clarify, to wrap up your flipped homework for tonight, you are trying these 4. See? All 4. Give them a try. Any questions, you can send me a remind, and I look forward to seeing what you got for answers on 3, 4, 5, and 6 at the start of tomorrow's class. Have a great night, everybody.